Okay, hi, this is my video number 24, I think, yeah, 24. As promised in the last video, that in this video I'll give you some example on how to solve the integral equation using a hilbert-schmidt theorem. Okay, now first example. This example, we want to solve the symmetric integral equation. We have symmetric integral equation. Solve ux x squared plus 1 plus 3 over 2 integrate minus 1 to 1 xt plus x squared t squared ut dt. Okay, using hilbert-schmidt's theorem. Okay, so that's the equation. Now, if we compare with the standard Freedom integral equation, we have standard Freedom integral equation. We have ux is equal to fx plus lambda integrate a to b kxt ut dt. So compare those. So what we have is that fx, so we have fx is equal to x squared plus 1. Our a is minus 1, b is 1. Our lambda is 3 over 2. And the kernel kxt equal to xt plus x squared t squared. So you can see from this kernel is actually symmetric, which is also the same as ktx. It's a symmetric kernel. So the main point in solving this equation using hilbert-schmidt equation, that first thing you need to consider the homogeneous equation. You need to consider the homogeneous equation. From there, we need to find the eigenvalue. Yeah? Then after that, we're going to normalize. We obtain the eigenfunction. Then we normalize eigenfunction with respect to each eigenvalue. Then we need to find f1, f2, and then from there you can set up the solution. All right, so let's begin this thing. So we have fx is equal to that. We compare with the standard Freedom integral equation. So we have all those data. Now, so we consider the homogeneous equation. Yeah. So consider the homogeneous equation, which is ux is equal to we have lambda minus 1 to 1 xt plus x squared t squared ut dt. Okay, of course from there you can split into two. You can split those things into two. You can write this as a we integrate respect to t, so we can take out x. So we have lambda x minus 1 to 1. We have t ut dt plus lambda x squared minus 1 to 1. That one t squared ut dt. Alright, now as usual we define these two integrals. So we define C1 as integrate from -1 to 1 t ut dt, and C2 as we integrate from -1 to 1 t squared ut dt. This one as a u1, this one as a C1, that as a C2. Okay, then from those, therefore we have C ux is equal to, we have lambda x, that one is C1, so we have lambda C1x plus that one is lambda C2x squared. And then we change x with t. The purpose is that so that we can substitute into that. So we have ut, so therefore ut for x equal to t, we have ut equal to lambda c1t plus lambda c2t squared. Okay, so therefore we have C1 is equal to minus 1 to 1 integrate t ut is given here, that, so we have t ut is lambda c1t plus lambda c2t squared dt. Okay, then of course from there you can evaluate this. That give you so lambda c1 integrate minus 1 to 1, we have t squared dt plus that one is lambda c2 integrate minus 1 to 1 t cube dt. Okay, and those you can evaluate those easily. Then from there you can have that C1 you factor out, bring it all to the left, so what you have is 1 minus 2 lambda over 3 C1 plus, for C2 we have 0, C2 equal to 0. And then we also do for the C2, and for C2 we have that integrate from minus 1 to 1 t squared, our ut is given there, we have lambda c1x lambda c1t plus lambda c2t squared dt. Okay, then that give you, we have lambda c1 integrate minus 1 to 1 t cube dt plus lambda c2 integrate minus 1 to 1 t to the 4th dt. Okay, and that we have c1 0 c1 plus 1 minus 2 lambda over 5 c2 equal to 0. Now bear in mind that even though you have that, do not find the lambda straight away, because you need to find lambda from those two solutions, from those two equations. Alright, not from that, because if you find from that, then you only get one lambda, you got one lambda here, which is not quite right. Remember that in order to have the non-trivial solution, the determinant of these two equations is equal to 0, right? So if you find the determinant of these two equations, that and that, okay, so let's say d lambda, the determinant, this is given as, we have 1 minus 2 over 3 lambda as 0, and this one is 0, 1 minus 2 over 5 lambda, that gives you 0. Okay, and then from there we have our lambda is 3 over 2, and our lambda 2 is 5 over 2. Thus from there we can obtain the eigenfunction you substitute into that. Where is it? Here we found what lambda is. Then we can have the eigenfunction. So therefore the eigenfunction is u1x that's equal to x, and u2x is equal to x squared. Okay, you should have no problem for the eigenfunction, I suppose. Now we need to normalize these two eigenfunctions. Okay, we normalize the eigenfunction, normalize the eigenfunction for the corresponding u1. Let's say we have phi 1 as a normalized eigenfunction x. This is given as u1x over integrate minus 1 to 1. We have u2x, I think here is u1x squared dx to the half. Okay, you solve this with u1 is x, that will give you sub 6 over 2x. Alright, then for second eigenfunction, we have phi 2 is given as we have u2x over integrate minus 1 to 1 u2x squared to the half dx to the half. That will give you sub 10 over 2x squared. And from there, once we obtain the normalized eigenfunction, we need to find f1 and f2, where f1, so therefore our f1 is given as we integrate from minus 1 to 1 fx phi 1x dx. That gives us integrate from minus 1 to 1. Our fx is x squared plus 1. Our phi 1x is that one we have 6 over 2x dx. Yeah, you evaluate this, that will give you 0. And then for f2, we integrate minus 1 to 1 fx phi 2x dx. That gives us integrate minus 1 to 1 x squared plus 1, and for phi 2x is sub 10 over 2 x squared dx. Yeah, evaluate this, that will give you 8 sub 10 over 15. Now, having obtained f1, f2, then we can construct the the solution. Yeah, so we have now, since our lambda 1 is equal, our lambda is equal to lambda 1, and f1 is 0. We have f1 is 0 there. All right. Therefore, there exists infinitely many solutions. Yeah, there exists infinitely many solutions, and the solution is given as ux is equal to fx plus a phi 1 x. Yeah, and plus lambda summation m from 1 to 2, because we have 2f here, so fm phi m x over lambda m minus lambda for lambda different than 1. So if you do this, so what we have that ux is 5x squared plus cx plus 1, where your c is given as a sub 6 over 2. Just follow those step by step. Remember that in Hilbert-Schmidt's theorem, we consider the homogeneous Freedom integral equation. Yeah, from the Freedom integral equation, homogeneous Freedom integral equation, we find the eigenvalue, then we obtain the eigenfunction. From the eigenfunction, we normalize those eigenfunction. Having done or having obtained the normalized eigenfunction, we need to find the f1 and f2. Then after that, we construct the solution. Now let's give the second example. A second example. Again, we use the Hilbert-Schmidt theorem. Use the Hilbert-Schmidt theorem to solve this equation. Ux is equal to x plus lambda 0 to 1 k xt ut dt, where kxt is given as, we have those x t minus 1 for x between 0 and t, and t x minus 1 for t x between x and x between t and 1. Okay, now we solve this solution. Compare with the standard Freedom integral equation. What we have, if fx equal to x, our a equal to 0, b equal to 1, and k is given as this. Yeah, k xt is given as those. Now we consider the homogeneous equation. Consider the homogeneous equation, which is given as ux is equal to lambda 0 to 1 k xt ut dt. And if you use the given kernel here, so that we can write u as we integrate from okay, so we integrate this from 0 to x, t from 0 to x. This is t dt, so I think this should be t here. This is x, and t here. That should be the correct one, right? Should be t, yeah. Just a minute, let me correct my notes. Tx xt. Okay, so we use the given kernel. Then we have this. We have lambda t. Just a minute. Okay, lambda t x minus 1 ut dt plus integrate x to 1 lambda x t t minus 1 ut dt. Okay, no, this is correct. Okay, sorry about that. This is correct. This is x t and t x1. That's for x. For t, this is obvious. Now, okay. Now, from having done those things, so we can differentiate this x, this u, or this equation here with respect to x. Yeah, if we differentiate those ux with respect to x, you can use Leibniz theorem. Yeah, Leibniz rule. Okay, you can use the Leibniz rule. What is the Leibniz rule? So differentiate this. I'll explain those things. U prime x, that's given as, we differentiate this, we have d dx integrate 0 to x lambda t x minus 1 ut dt plus integrate differentiate those x to 1 lambda x t minus 1 ut dt. I just copy the u that we have above, that we have. Okay, now the how to differentiate this. So this equal to, we bring this differentiation into the inside of integral. We have 0 to x, we differentiate those with respect to x, the del x. Okay, then those we have lambda t x minus 1 ut dt, yeah, ut dt, differentiate those, that's dt for the integral, and then plus, now this is the Leibniz rule. Yeah, we evaluate at lower bound as well as upper bound. So we have lower limit and upper limit. So we have lambda x. Okay, so lambda x minus 1 okay, u1, lambda x minus 1 u1. Here we have a t equal to 1, right? We have t. Okay, so t is equal to x. So this is x. This is the our terms. So that's we differentiate respect to x, and then the next is if we evaluate at point at the upper limit x. So we have lambda x. We have lambda x minus 1 ux here, ux. Okay, and then we differentiate those limit. So dx dx, because the limit is x, minus we do the same for the lower limits, that we have lambda that should be 0. We have x minus 1 u0, then we differentiate 0 with respect to t. Okay, so that's the first integral. Alright, so this x. Alright, and then plus the second part here, we do the same, del x, integrate x to 1 first, x to 1, del x. So we have delta x t minus 1 ut dt plus we have lambda x 1 minus 1, yeah, we evaluate that upper limit 1 minus 1 u1 and then differentiate the upper limit with respect to x dt, dx. And then next at the lower limit, so we have lambda x x minus 1 ux dx. As you can see from there, what left is that, so this is, that cancel out with that because this is minus, okay, that cancel out with that give you 0, and that give you 0, and then this is 0, this is 0, this cancel out with that, what left is only those two. Alright, so you have integrate 0 to x lambda t, just differentiate that with respect to x, so lambda t ut dt, and plus integrate x to 1, integrate that with respect to x, so we have lambda t minus 1 ut dt. Alright, now if you differentiate again this integral, you differentiate again, so that gives you u double prime. Now let me write those. Differentiate again with respect to x, that gives you u double prime x, that's equal to, you differentiate those things, d dx, integrate 0 to x lambda t ut dt plus d dx, we integrate those x to 1 lambda t minus 1 ut dt. Okay, and then follow the same process as above. This is equal to, we integrate from 0 to x, differentiate that with respect to x, del x, everything there, lambda t ut dt, that plus then we evaluate at point x. Let me check those things. So we have lambda x u x, correct, and d dx minus, we have lambda evaluate at t, yep, correct. So evaluate those t, so now at 0, so we have lambda 0 u0 d0 dt, that the first term. Okay, the second term, second part, you have integrate x to 1, we have del x lambda t minus 1 ut dt plus upper limit, we have lambda, the upper limit is 1 minus 1 u1 dt d1 dt minus lower limit we have lambda x minus 1 ux dx dt. Okay, so if you evaluate those, respect to x, this one is 0, that one respect to x, that gives you 0. So what left is actually you have minus u double prime x minus lambda ux equal to 0. So what we have done there is that we reduce the Freedom integral equation into the differential equation, just ordinary differential equation. And then from u, where is our u? From u, there you can find the boundary condition. Yeah, the boundary condition. We have u 0 equal to 0. You have u1 equal to 0. Just substitute into the u here. Yeah, this one. Then you can find the boundary condition for u. Alright, now we're going to find the eigenvalues and eigenfunction. In this case, of course, because we involve the differential equation here, ordinary differential equation, this is just a standard. I think you know this thing. So we need to consider lambda 0, lambda is positive, and lambda negative, and find the eigen value and find the eigenfunction. Now from here, let's consider first, let's say I call it case 1. Case 1, we take lambda equal to 0. Yeah, for lambda equal to 0, what we have, lambda, we have u double prime x is equal to 0. That gives a solution ux is equal to ax plus b. Yeah, you just integrate twice, that you obtain those things. Then from there we use the boundary condition. From the boundary condition, we have a equal to b equal to 0. Okay, so therefore from there we have, so therefore the solution is ux is equal to 0, which is a trivial solution. So there is no eigenfunction, so no eigenfunction, and therefore no eigenfunction, and lambda is not the eigenvalue. Alright, that's the first case. Then for the second case, we consider case 2. We let lambda equal to k squared, where k is not 0. Alright, and then from our differential equation, so therefore we have u double prime x minus kx squared ux that equal to 0. Right, and then from there we obtain the general solution. The general solution is given as ux is given as a e kx plus be minus kx, and then again we apply the boundary condition. Yeah, from the boundary condition we have again a equal to 0 and b equal to 0. Then we have ux is equal to 0. Again we have a trivial solution, so therefore no eigenfunction, and lambda is not again eigenvalue. Now for the third case, case 3, we let lambda equal to minus k squared for k different than 0. Of course, because when k equal to 0, that goes to case 1. Alright. So then we have our equation is u double prime x plus k squared ux that equal to 0. Okay. From that you get the general solution. The general solution is ux is equal to a cos kx plus b sin kx. Alright, and then using the boundary condition, we obtain that b equal to 0. And also we have b sin x that b equal to 0. So we have sin kx that give you 0, and from that you can find our lambda is actually minus n squared pi squared. Okay. Now, having obtained those, so therefore our eigenvalues is given by lambda n is equal to minus n squared pi squared for n 1, 2, 3 and so on. And therefore we have our eigenfunction that ux equal to b sin n pi x, and then you can set b equal to 1, that give you ux is equal to sin n pi x. So that's the eigenfunction. Then we normalize the eigenfunction. So what we have, phi n x is, we have un, again this is we have n, so let's say this un, so un x over integrate from 0 to 1 un x squared dx to the half. So if you substitute into there, you will find this given as sec2 sin n pi x. Alright, now having obtained the normalized eigenfunction, hence we find the fn. So fn x is given as integrate, this is fn, not fn x, so fn 0 to 1 fx phi n x dx. Okay, substitute everything. We know what fx is. We substitute phi n. Our fx is given as I don't know, where is it now? Our fx is x, right? So this is equal to integrate 0 to 1 fx is x, phi n x is given here. So that's sec2 sin n pi x, this is sin, alright, dx. So you do all this process. This is not difficult. You can I think use integration by parts, or yeah, integration by part may be the best. And then we obtain the solution minus 1 n plus 1 sec2 over n pi. Alright, so now we can develop the construct the solution. We have a two situation here, right? Situation 1, situation 1, that we let our lambda is different than lambda n. So in this case, we have our ux is equal to fx plus lambda sum n equal to 1 to infinity fn over lambda n minus lambda phi and x. And then you substitute everything you got here. This gives you x plus 2 lambda over pi sum n 1 to infinity minus 1 n sine n pi x over n squared pi squared plus lambda. Okay, and then for situation number 2 is as done already. As done 2, situation 2, we let lambda equal to lambda n, which is equal to minus n squared pi squared. Yeah, for all n as a natural number. Yeah, just for all n, 1, 2, 3, 4, 5. Yeah. Then from there we have fn that gives you 0, and hence the integral, the given integral equation has no solution. Okay, so now I given a very specific example, and some are quite easy, some are quite tedious to solve it. For the freedom integral equation, we solve using the hilbert-schmidt theorem. Alright, so with that I end up this video. Bye bye.